All right. Hi, everyone. Thank you all for coming. I was hoping to play some Pink Floyd on the audio here, but that didn't quite pan out. But anyway, you will notice probably, if you know them, that this is a Pink Floyd-themed talk and not so much an X-Files themed talk, as the title might have suggested. So, during this talk, what I would like to talk about is distributed systems, and more specifically, the viewpoint of a single cluster node like this in a cluster. And so let's start right away with a little bit of a disclaimer. Because you know what you're doing as a distributed systems engineer, you read a lot of papers, and papers have this property of being recursive. So you start reading a paper, and then in the paper there are some references, and you start you like some of the references, and so you also get these papers, and you print them and read them, and sure enough, you end up with a big stack of papers after a while. And then at the same time, you have to make some money, because you don't make money reading papers. So you eventually you're building also a distributed system like that one. But you know that takes some time, and maybe works and maybe doesn't. And then as the year go by, your sanity slowly leaves you. And I just mentioned that because I'm fine with this constant feeling of doom and existential crisis that comes with getting a bit too deep in the world and realm of distributed systems, but you may not. So please don't come to me in 5 years saying that I ruined your life because you got interested in the distributed systems and complain, because I will have warned you. A bit about myself. My name is Manuel Bernhardt. I'm an independent consultant. I specialize in reactive systems, which is to say systems that are built mostly with Akka, the Scala or Java language, the Play framework, or the Lagom framework. And what I do is either my clients fall in two categories. Either they come to me before or while they're building the system, and that's the good case. And then the other case is they come to me after they launch the system to production, and then they come to me with a certain sense of urgency because something doesn't work as they would have expected. I also train. I'm a Lightband partner, and I train on the topics of Akka Cluster, reactive streams. So that's what I do for a living. And you know, other than that, I also like to scuba dive. And this is not the Danube, I wish. Yeah, so let's start with some motivation here. Life is a single-player game. You're born alone. You're going to die alone. All of your interpretations are alone. All of your memories are alone. You're gone in 3 generations, and no one cares. Before you showed up, nobody cared. It's all single player. So that's a very nice quote by Naval Ravikant, the CEO of AngelList. Are you all motivated now? Yeah? Okay, great. No, I didn't actually try to motivate you here. I'm trying to motivate the talk, because you can take this quote of a single player game and apply that one-on-one to the life of a single cluster node, you know, because that's what a node in a cluster is doing, is looking at these other computers. And when we think about a cluster, we like to think of them as being this well-defined. We know there is these 3 little Raspberry Pis here, and they all are part of our cluster. This is what I would call the God view, because we know it all. But the reality of building distributed systems is that you don't reason in terms of all the whole of what there is. You reason in terms of one machine that sees other machines through a network. And that network is gonna be unreliable. We haven't managed to build non-unreliable networks yet. So, you know, it may just happen that your network is gone and then you don't see the other node. And that is something that you have to think about when you're building distributed systems. And this is what I want to focus on during this talk. So really, when you want to build a cluster, there's 3 things you need to be doing. First one, you need to have a way to tell who is there with you in the cluster, who is joining, who is leaving. who is there, who is part of the group. Then, nodes can crash. Either the process crashes, or the hardware fails, or the network fails. They're gone. So you need to figure out who is in trouble. It's the failure detection part. And then finally, in some cases at least, maybe in most cases, you're using a cluster because you can't fit it all on one machine. You may use a cluster for fault tolerance so that you can still continue working when one of the nodes fails, but more often than not, you also want to use a cluster because you want to scale out on many machines because you have too much load. And then the question is, how do you balance the load across all of these nodes? Who can take up new work, etc. That's the load balancing. And it turns out there is one abstraction that you can use and that makes building and reasoning about all of this a lot easier, and that is the abstraction of group membership. Who is there with me? If I have a service that runs on every node in the cluster and that tells the application who is part of the cluster, that makes building distributed systems a lot easier. You basically put this abstraction in there, and it's a nice abstraction that you can use on an application layer then to build things. And then so let's look at what you need in order to implement group membership, such as service. You need three things. You need failure detection, figure out when someone is crashing. You need a way to tell other nodes that something has happened. For example, that you have been contacted by a new node that would like to join the cluster, or that your neighbor just told you they want to leave the cluster, or that you just figured out that another node you were monitoring has gone away. You need to disseminate this knowledge. That's the second thing. And then the third thing is that you need to reach some kind of consensus as to who is there and who isn't in the cluster. So you need to reach consensus as to the list of nodes that are there with you in the cluster. This is the third thing. It's pretty much also hard, or in some ways it's also quite impossible, as we'll see, but we'll get there in time. So I will start with the failure detection part, which is, I don't know why I developed this irrational obsession with failure detectors some time ago. So what are failure detectors? Let's look at the definition here. There's two key properties of failure detectors. First one is the one of completeness. And that means that if a node crashes, all the other healthy nodes in the cluster that haven't crashed should know about the fact that that node is gone, so that there is no node that will still try to talk with that one, although we know it's gone away. That's the first one. The second one is accuracy, which is to say that if there is no healthy node that should be suspected by another healthy node of having crashed, or in other words, there are no false positives. You don't want your healthy nodes in the cluster to start suspecting one another, even though they're perfectly fine. And then, there is reality kicks in, and you have these pesky little things like speed and network message load that you also have to think about when you want to implement a failure detector in practice, because if you don't think about them, your failure detector is going to be pretty much unusable in a real-world system. But we're not going to use these two properties to classify failure detectors further on. Now, as it turns out, when you do distributed systems engineering, there is this category of proofs called impossibility results. So these are very smart people that prove things that are impossible to achieve. And it turns out that it's impossible for a failure detector algorithm to deterministically achieve both completeness and accuracy over an asynchronous unreliable network. So an asynchronous unreliable network is the kind of networks we work with. So in other words, we're doomed. We can't have both of them. So what do? Well, we make trade-offs. That's one thing we do in many parts of computer science, and in the realm of distributed systems, we make a lot of trade-offs. So we talk about strong to weak completeness, where either all or some of the non-faulty members detect a crash, or we talk about strong to weak accuracy, where there are no or some false positives. We can't have it both. But we can make some trade-offs. And in practice, what happens is most applications, they want strong completeness. They want everyone to know about nodes that have failed. and they choose a weaker form of accuracy. So there's two ways in which you can implement failure detection. One is to use a heartbeat. So a node that's being monitored will send a heartbeat out to the monitoring node every now and then, or every second, let's say. And when they stop heartbeating, we know the node is gone away. There is a problem. There is another approach used by, for example, Akka Cluster, where you have a ping pong. So a monitoring node will ping a node, and there needs to be a reply so that we know that the other node is healthy. So these are the two sort of strategies that we can employ here. Okay, so now that we looked at some definitions, let's look at some failure detectors. The first one I want to talk about is the Phi adaptive accrual failure detector. So the first property of this failure detector is that it has a very cool name. It's also an adaptive failure detector, which is to say that it tries to adapt to changing network conditions. So when the network conditions changes, the failure detector also sort of figures that out. And that's quite important because in real life, networks also tend to change, especially if you're in the cloud. And if you look at how network load and so on in the cloud evolves, it's on shared medium. It's quite interesting. And what the Phi accrual failure detector, what it does, it introduces this notion of accrual failure detection. So accrual means that instead of having a failure detector that is Boolean, which is to say either a node is trusted or it's suspected, here you have a spectrum. Okay, so the failure detector gives you a suspicion value, and you or the application then makes a decision as to what it does with that value, when it starts to take certain actions. And we can see here that the lower the value, the faster the detection time. Okay, that's nice. But then on the other hand, the lower the threshold value, the higher the mistake rate. The mistake rate is this accuracy that we were talking about before. So you start suspecting processes that are perfectly healthy of not being healthy. And so the way it's described in the paper is that, for example, the example they give is a master and some worker processes. So the master distributes the work, and what you could say is, well, if my suspicion level grows over 8, I'll stop sending new work to that node. If it grows over 10, I'm going to send the work that guy was supposed to do to some other node, and then over 12, it kicked them out of the cluster. I removed them entirely. That's the idea of this accrual value that sort of accrues and changes in time. So I would recommend, if you want to learn more about failure detection, the paper is quite interesting because it sort of gives you a broader idea of what failure detection is about. It's a very nice introductory paper if you want to get into this stuff. Another failure detector, the name is not that cool, but it's a new adaptive accrual failure detector. So it's new. It's a bit newer than Phi, and mostly this one is about. It's much simpler to implement than Phi. It's using. It still gives you a probability, a suspicion value, but the most interesting thing. So I implemented this one for Akka Cluster, and what I found is that it's more adaptive. It's better when it comes to changing network conditions. Or to put it bluntly, when you run this thing on a longer time frame on AWS, which goes yo-yo like on the network, this one is better off. It will have a better, an easier time there than Phi. But that sort of is still the same idea of accrual failure detection. It doesn't really innovate in the way in which it suspects things. So there is one that's very interesting called the swim failure detector. As you swim lazily through the milieu, the secrets of the world will infect you. The idea, this failure detector, and in fact it's not only a failure detector, it's also a dissemination component, is it's built on biology. It actually cites a biology paper. It's about epidemics and how infections spread in a network. So we'll get to that when we get to the dissemination part, but so it uses this analogy of an infection. And the idea here is to say, okay, it's one thing to build a cluster that has 10 or 20 nodes, is another one to build a system that has 100, 200 nodes. How do I build that? How do I scale? So the idea of Swim was to have a scalable membership protocol that could give back the same speed and same network load, or like not exponential growth as the number of nodes increases. And one technique that they use is to say, okay, if someone fails, we're not gonna remove them right away. There's two mechanisms. The first one is that if a member is suspected of failure and it receives a gossip message saying that it has failed, it has a chance to say, hey, I'm still alive. Why do you say that I'm gone? So that's one technique. The other technique is indirect probing. The way that works is one node will ping at random another node in the cluster. And then for some reason, the acknowledgement does get lost, or something is wrong with the network, or more realistically speaking, the node being pinged runs Java, and there is a garbage collection, and then there is no answer for 1 or 2 seconds, which is enough to sort of trigger a false positive here. So what this node then does, it will issue ping request messages to other nodes, also chosen at random, which in turn will try to ping that node that is being suspected. And then eventually one acknowledgement may make it back, and that is being forwarded to the initially requesting node. And then we know, okay, this guy is still there. I just couldn't reach them directly for whatever reason. So the whole point of this is to reduce the amount of false positives to get a stronger level of accuracy. Now the problem is that in practice it doesn't swim, it sinks. In practice there's still too many false positives with this approach. And so I don't know if anyone knows a company called HashiCorp. They do things like Console, Terraform, Vault, Vagrant. And so they have distributed systems. I mean, Console is a distributed system service discovery. And so what they did, they tried to implement Swim. That's L0 up here. And they got a lot of false positive events here. You can see it's quite a bit. So what they did, they implemented a thing called Lifeguard. And they added a few extensions to the Swim protocol, and they managed to, when you activate all of them, they managed to get to less than 2% in terms of amount of false positives on the as compared to Swim. So this is really quite something they've done here. The implementation of their membership layer is open source. It's called MemberList. It's written in Go. You can go fetch it on GitHub. I haven't found anything more recent than that in terms of failure detector mechanism approaches. This is from 2017. This is fairly recent. So if you want to go and build a membership service, don't start with Swim. I mean, build on top of Lifeguard. This is what I would say. Okay, so that was the part on failure detection. Now let's take a bit of time and talk about dissemination. And anyone knows the name of this album? Yeah, it's Pink Floyd, but no, Division Bell. So sorry, I'm probably the Pink Floyd geek in the room here. So the question here is, how do we talk about things? How do we disseminate things in the cluster? How do we spread knowledge in the cluster? How do we talk about members joining, about members leaving, about members having crashed? And so there is 2 strategies here. The first one is multicast. So that could be hardware multicast, that could be IP multicast, that could be UDP multicast. But it turns out that there is 2 reasons why this isn't that popular. The first one is that if you go to your sysadmins in a data center and you say, hey, I want multicast, they will look at you and they say, no. Well, maybe not all of them, maybe not all data centers, but many data centers. And I've seen that at client sites where they say, yeah, but we can't do this multicast UDP discovery of members joining, or because our admins won't let us do that. So that's one real world restriction that's there. But even if that wasn't the case, even if you had very nice sysadmins that were going to go and configure hardware multicast for you because they love you so much, even if you had that, there turns out that building distributed algorithms that use multicast is surprisingly hard, because you don't have this guarantee that everybody gets the message. What do you do if a few members don't get the message? If they have failed while the message was on the way? So multicast happens, there is like a big, very long compilation of algorithms that talk only about multicast that shows that this is extremely hard to prove and to make work in practice. So what happened is instead people started looking into another way of doing things, and this one was implemented or researched actively in the days of peer-to-peer. Who remembers Napster? Kazaa? Yeah, Kazaa. Yeah, it's all very legal. So what happened there was a lot of research done there, and that's when gossip protocols, because the question there is like, I'm searching for this MP3 file. How do I span across the peer-to-peer node? How do I search? How do I disseminate things in my peer-to-peer cluster on the internet? How do I make that efficient, etc.? Many nice things that came out of that Cord, amongst others, many papers to read there. And so let's talk about gossip a little bit. The idea with gossip is that a node will gossip with, or the idea of random gossip is that a node will talk with one other node in the cluster. So at every tick of the clock, so let's wait here, at T0, I talk with one, and then at T2, these two, they talk to other ones at random, and then T3. And then you see that it takes only 3 ticks of the clock, let's say 3 seconds, to get the word across a 5-node cluster. And it turns out that this scales very well, only if you only talk to one node at random in a cluster. So this was proven in 98 by Van Renesse et al. This sort of random gossip style. Then in 2000, we have a paper that talks about a few more, something that's a bit more deterministic, okay? Round-robin gossiping, because random gossip is not quite deterministic. You don't know what's going to happen. So round-robin is one option. Binary round-robin is something that performs a little better. And then round-robin with sequence check is where you actually use the fact that it's round-robin, and so you should be able to tell who is supposed to have received a message by what round. And based on that, you can fail them faster or slower. But for some reason, this hasn't been very popular. I haven't seen this picked up in more recent research. And it turns out that people always go back to random gossip. I mean, Dynamo or other, they all went back to random gossip. Actually, Dynamo does local gossip, so that's even another thing. So and the third type of gossiping here is this, say, okay, well, I'm going to piggyback on something else. So for example, that Swim does that. Swim has this failure detection protocol where anyway they're going to probe another node at random every protocol period, every second or every 2 seconds they're going to talk to someone else. And so instead of just sending a ping here, up there, or an ACK, they actually piggyback information on top of these things. So I send you a ping, but I'm also telling you that I know about these 5 other members. And then in my ACK, I also tell you that I saw this other node 3 seconds ago. So it uses another protocol. So they call this infection-style gossip. And that is also a very interesting approach, because you have less messages you send less stuff around. It turns out that Lifeguard, so that's the Swim paper, but Lifeguard said that, well, after all, we need gossip to be something periodical. We want to do that faster. So Lifeguard went back to gossiping every few seconds anyway, or whatever you configure it to. So these are like sort of 3 approaches, and the most successful is the random gossip. But then what do you gossip about? What's the point? So let's say we have a node A, and the A maintains a list of all the other nodes it knows about, A, B, and C. And then A has seen A 0 seconds ago. A has seen B 1 second ago, and A has seen C 3 seconds ago. That's my list in viewpoint of A. B has seen A 3 seconds ago, has seen B 0 seconds ago because I'm B, so I know that I'm alive. And then B has seen C 1 second ago. And now if A gossips to B, if they both exchange their gossips, when you sum these things, what you end up with is A and B have seen each other 0 seconds ago and have seen C 1 second ago because B saw C 1 second ago. And this is how you spread. So this is sort of a way to do failure detection using gossiping. And the idea here is to say that if what I see here is if this value gets more than say 5 seconds, 8 seconds, whatever you configure it to, you consider the node faulty. This is how you can say, okay, nobody heard about this guy for 5 seconds. I'm gonna say they're dead. We can't trust them anymore. So that's one thing you gossip about. So there is a few ways in which gossip can be optimized. Akka Cluster, for example, what they do is Akka Cluster maintains in the gossip message a list of who has seen this gossip at a certain version. So what they can do with this information is that they can gossip with a higher probability to nodes that have not yet seen that gossip message. And that way they spread things faster. So they gossip with an 80% probability to nodes that may not have seen the latest version. With larger clusters like 400, above 400 nodes, you want to reduce that probability because it starts to get a bit messy. But that is one optimization there. Also, like a cluster, what they do is when less than half of the nodes have seen the latest version. So that happens, for example, when you bootstrap a cluster or when there has been a network partition and you have to repair that. Then the node, when they notice that less than half of the nodes have seen the latest version of a gossip, they will start to gossip faster. They speed up the gossip. They gossip 3 times as fast. And then when the cluster converges again, when everybody has seen the latest version of a gossip, they slow down. Lifeguard, what they do is they have this anti-entropy mechanism where they will take a node at random and do a full sync via TCP/IP. Okay, because in Lifeguard, what they use is UDP, but UDP might get lost. So what they do, and especially after network partition, when the network, when both parts see each other again, you're in this sort of unstable state and you want to repair things faster. So what you do, you use convergence, you use this full sync to make things well again. And now let's talk about one of the hardest things in distributed systems, which is consensus. Or in the context of this talk, consensus means how do I make it so that every node knows about all the other nodes. Everybody has the same idea of what the cluster is. This God view, like when you have 3 of them. Well, I can't hold them up, but here you see 3, so everybody should see the 3 nodes. Okay, how do I reach consensus? So let's start with impossibility again. The impossibility of group membership. And the idea here is that the primary partition group membership problem cannot be solved in asynchronous systems with crash failures, even if one allows the removal or killing of non-faulty processes that are erroneously suspected to have crashed. So what that means, primary partition is like we have this main partition, or ideally we only want one partition, okay? If we have 2 or 3 partitions, it's not so much interesting. How do we build an application on top of that? And then for a long time in the research community, there was this belief that if you let nodes sort of, when they suspect one, if you let them remove that one suspected node and say, okay, they're gone, then you could still have this primary partition, this nice world where everybody is there. But it turns out that this was proven to be impossible in 96 by Chandra et al. On the impossibility of group membership. That result itself is based on another result, which is very well known in distributed system, the FLP impossibility result. So the point here is the moment that you have one, it's enough for having to have one process that has crashed in an asynchronous network so that you can't reach consensus anymore. So again, we're doomed here. We can't reach consensus. How do we even build things that work? And so what we do, or what we take of it, what this means for us is that if we build a cluster-based system, it wouldn't be very smart of us to make membership-related decisions while the cluster is unstable, while there are some nodes that are suspected to be failed. Because the moment that I have someone that is suspected of having failed, I don't know if my message has reached them. So that means we need some coordination, or we need to make something there. And so the rest of this is about how do we work around? Again, it's how do we work around the fact that we can't really reach consensus, but we need it in some way or another. So the first thing when it comes to reaching consensus that's really sort of vital and annoying and it always comes back biting us is how to reach consensus about the time. So and there's a very nice paper by Leslie Lamport, Time Clocks and the Ordering of Events in Distributed Systems. This paper has won a Turing Award. It's one of the most cited, or maybe even at some point it was the most cited paper in computer science. And what this paper introduces is, it introduces many things, but amongst others, it introduces the notion of logical clocks, also called Lamport clocks. How do I order events? How do I tell that an event that took place on one node happened before or after another event that happened on another node? How do I create this order? And there is a notion of a logical clock, which is a counter, basically. It's not anymore a physical clock, because not everyone is Google. Not everybody has GPS and atomic clocks in their data centers, like Spanner has, where you can then create a nice order. And even Spanner, I don't know how many of you have heard about Spanner. Even Spanner has a 7 milliseconds span where there is no total order. So even Spanner is not absolute in that way. So this is using the a causal sort of view to order. Now it turns out that Lamport clocks are not enough if you want to tell that two events happened at the same time. It can tell you that they happened after or before, but it can't tell you that they happened at the exact same time. So if you want to do that, you need vector clocks. And vector clocks are vectors of Lamport clocks. So each node in the system knows which version, of the clock the other nodes in the system know about currently. And that's how you can detect conflicts. So to make things a little bit more confusing for you, there is another sort of paradigm that was developed independently, but is pretty similar. It's the one of version vectors. And these two guys, vector clocks and version vectors, are very often confused. Vector clocks are interested in the semantics of how do you order events in a distributed systems, and version vectors are interested in the semantics of when you replicate data in a distributed system on various nodes, and this data is being modified on two nodes concurrently, how do you detect conflicts there? That's version vectors, and there is this blog post here, 15, which is version vectors are not vector clocks, which sort of disambiguate these two things. They're extremely similar, but slightly different. And it turns out that version vectors are not enough because they have false positives. So if you really want to build on version vectors, you don't use version vectors anymore. You use dotted version vectors, which prevent false conflicts that may, it will say that two things are in conflict when they're not in conflict. That's dotted version vectors. And no, that is basically research on finding conflicts in distributed data, which brings us to the question, is this stuff actually relevant in practice, Or is he just talking now about theoretical stuff that sounds fancy, but that's it. And it turns out, yes, you can use that in practice. Finally, some code. So here what we have is a gossip message. And the gossip message has members, who is in the cluster. We have an overview, and we have a version. And the version here, that's a vector clock. And why is that a vector clock? Well, because you have to tell if nodes that have seen things happen independently of one another, if they have all seen the same events, because they may have seen them happen maybe there is a new node that joined a cluster, and some nodes learned about it before others, because remember, we have this random gossip, so the information may spread in a different order, but overall we want to tell, does everybody know about everyone else? And that's where you use a vector clock in Akka Cluster to tell, okay, if this node has seen this version, you can tell that they've seen the latest version. What you can do with a vector clock is simple. You know, if I'm a node here and I'm receiving a gossip, an Akka gossip with a version vector, I can say, okay, this new gossip that I just received is newer, so I'm going to update my information. Or this gossip that I received from this node is older, so I'm going to reply to the guy and tell him, look, there's a newer version here, grab it, use it. Or maybe the two versions conflict. It's conflict detection we talked about. And when they conflict, what you have to do, you have to merge both worlds. Maybe one gossip talks about a new node having joined, and the other gossip talks about another node having left. So you merge these two things, and then you create a new version. That's the new version of reality, and you gossip about that one. So these things can be used in practice and are very useful in practice. So while we're talking about conflicts, there is an awesome thing called conflict-free replicated data types. So the idea of CRDTs is that, and we talk about strong eventual consistency, is to say, okay, I have my data structures, and my network may be partitioned for some time. There is data being written in two parts of the network, and after the partition is resolved, I will not have a conflict, because what happens is if I'm talking here and I'm talking there, independently of one another, usually I'm screwed, right? How do I merge? And with CRDTs, these are data types that always resolve to something. There's two families. There's the ones that use commutativity of operations, where you say the operation plus 1 plus 2 equals 2 plus 1. That's the property that CRDTs use. And then there's another one, the CRDTs. They use convergent of state. There is a function, a merge function, that has to be monotonic, which is to say it only grows in one direction. And in this example, this is a state-based CRDT. It's using max. So let's walk through this. I have my three nodes here. Like I have 1, 2, and 3. And we start here, and node 0 sets this value to 1. Node 2 sets the value to 4, and node 3 doesn't set any value. So I'm first going to talk to this third node here about 4, and in order to merge, I'm using the maximum between 4 and 0, so that's going to be 4. Then here, I'm going to talk about my new value to that other node up here, and it's going to be the maximum between 4 and 1, so it's going to be 4 again. And then here, I set my value to 4, so I'm talking to this node here. It's a maximum of 4 and 4, so it's going to be 4. At the end of the day, everybody sees the same value. It's 4 everywhere. And this may sound a bit esoteric, and it is, but there's more and more CRDTs being discovered, sets, maps, things like this. So it's getting easier and easier to build things on top of that. They're extremely powerful, and it's a very active field of research there. Now let's step back a little bit and talk about mechanisms that are used when you want to reach consensus in a more general way. And the idea here is to use replicated state machines. Everyone knows what a state machine is? Yeah. So any sufficiently complicated model class contains an ad hoc, informally specified, bug-ridden, slow implementation of half a state machine. So very often we don't like to build state machines. It's like we prefer to build our own stuff. And then when it grows way too complex and we have solved 152 Jira tickets, then do we realize that maybe we should have built a state machine to start with. And that, again, is a concept that has been expressed the first time in Leslie Lamport's time clocks and ordering of events in a distributed system. And it's the idea of using a replicate state machine. So what do we have? We have 3 nodes, and we have a client down there. This orange thing is a client. And the orange thing wants to send a value, let's say a bank transaction, for example. It wants to make sure that, that it's not going to get lost. So we want to make sure that in our distributed systems, we all agree on this value. Okay, it cannot be a different value in any of the other nodes. So what we do is we may send a few operations or events up here, like plus, minus, plus, whatever. And then each node has a state machine. And we know how to preserve the order between these events. So we're going to apply the same event to all the other nodes, to all the state machines and all the nodes. So what happens then, since they all start with the same state and they all get to see the same events in the same order, then we will end up with the same state in our distributed system, and then we are safe. We know that this value is now being replicated, and we know that if one of the node dies, well, we still have 2 other nodes that keep the same state. And that's a pretty fundamental idea to build these replicated state machines. Turns out that that is the theory, and in practice, it needs a little bit more to get there. Okay, so to get there, what we need is something called consensus protocols. How do we make it so that multiple servers agree on the same value? You may have heard of things like Paxos, yeah, Raft, Caspaxos. Nobody. That's normal because it just came out 2 weeks ago. So what's Paxos? So Paxos is sort of this original consensus protocol, and it turns out that this was very difficult to understand. So the paper came out in '98, and then in 2001, Lamport was at a conference, got fed up with people telling him that Paxos was too hard to understand, rounded up a few people and explained them Paxos again, and then he took these notes and published this paper, Paxos Made Simple. And then 13 years later, there was another paper published, another protocol called Raft, and the paper is called In the Search of an Understandable Consensus Algorithm. So it turned out Paxos Made Simple was not simple enough yet, so Raft was there to make it simpler. Basically, the idea of the whole idea of the paper was to make a thing that was easy to teach and understand. But it's still complex, okay? So you've got the notion of a commit log. If you look on the right-hand side here, you have this commit log, you have a leader and you have followers, and every period you elect a new leader, and there's a whole set of things. So everything is there, and there's a notion of committed entries, and you want to make sure that the committed entries are going to be the same everywhere. There's no way to roll back or anything like that, okay? So it's hard to understand. Okay, Raft is easier, but it's still difficult. And then fairly recently, Caspaxos came out, which is very interesting because it basically removes the need for log and the need for leadership and election. So it makes things a lot easier. It uses functions, and you don't talk about values anymore. You don't transfer values. You transfer functions. I think this is going to make waves. It came out, I read about it on Twitter 2 weeks ago. Very interesting paper, a bit raw, but I think this we're going to hear about it a little bit more. But still, consensus protocols require a lot of work, and of course you need them if you want to make something that's really safe. But it's hard, and if you heard about maybe the Jepson series by on the blog, the website is called afir.io. So it's still, many implementations are wrong. So my preferred way of reaching consensus is by convention. And that is to say, you don't transmit any information at all. So for example, a very elegant way of doing this is by the means of leader election, actually leader designation in Akka Cluster. What you have is, in fact, what you say is, I am going to order all the nodes in my cluster by IP address, and I'm going to put the ones that are not fit for leadership, for example, the nodes that are leaving or exiting or something like that, I'm going to put them at the end. So I have my order and I pick the first one. So I just locally order all my nodes. And so by convention, I know who is going to be the leader. I don't need to talk about it. I just know, everybody knows. And that's very elegant, I find. It also means that it's the leader that has to make some membership decisions of like who is up and who is down, etc. But it's quite nice, this way of doing things. So I think we have a few minutes left, maybe 3 minutes left. So let's talk about Akka Cluster very quickly. Akka Cluster, the architecture is simple. You have a membership part in the bottom. That's what actually is the cluster module, is this membership where you have a failure detector. So Akka Cluster uses the phi adaptive accrual failure detector. It uses this ping pong strategy for doing failure detection. Every node monitors 5 other nodes with ping pong by default. For the dissemination, it uses random gossip, but it's biased towards nodes that haven't seen a latest version of a gossip yet. And then for consensus, there is this convention of who is the leader. And then it's also the leader of the cluster who is making the decisions, who is deciding who is up now, who is part, who is leaving, who is left, etc. It also means that while there is some nodes being suspected of failure, the leader cannot do anything. So we have this bottom layer here, and on top of this we have a few modules, distributed data. These are CRDTs, pretty neat. Singleton means you only have one thing in a cluster, okay, singleton actor. Then you have sharding, where you can shard your actors. And Akka is all about actors, so you shard them across many machines. And then on top of that, finally, you build your application. So let's look at an example in practice. How does it look like when you are a member node in Akka Cluster? Okay, in the nice cases, I'm joining, I'm up because the leader said I'm up, because everybody else knows that I'm there. Then I'm leaving, and then the leader says that I'm good to leave, and I'm exiting, and then I'm removed. That's my happy case. My not so happy case, or in other words, reality. I'm joining, I'm up, and then something happens, the failure detectors sees that I'm gone. I'm in this pseudo state, which doesn't really exist in the state machine. It's just, I'm not reachable. And then I'm down, and I'm removed. And then, of course, the question is, how do I get from being unreachable to being down? Who is making this decision? And it turns out that this is it's not the failure detector, it's not the leader. But either I have to do it on my own, so I have an ops team that's there 24 hours, 7, that makes its decision of downing, of removing explicitly someone from the cluster. Remember, nobody can join or leave while there is a suspected node, because the leader cannot, because of all the things we talked about before. We need this to be explicit somehow. And so this is the category of protocols called, known as split brain resolvers, split brain resolution. How do I make sure that so how does that work? Well, it turns out that we are out of time now, and split brain resolution protocols would be another talk on their own. So what I invite you to do is go and check my blog from time to time, because I intend to write about this in more detail there. And yeah, so I cannot explain the magic or the algorithms there. It turns out that this is not too difficult to implement, but it's hard enough so that all the open source implementations of split brain resolvers for Akka that I've seen so far, they're all wrong. They're all buggy. So don't use them. And so, or use them but fix them while you are using them, or write your own that is correct. Yeah, so if you want to learn more, here at the end of the slides, which I will put online, you have all the papers that have been harmed while creating this slide deck. So you can go and read these all and more. There's more, but I didn't put them all here. So yeah, that's pretty much it. I hope you enjoyed this. I hope you learned a little bit, and yeah, thank you. And I don't know if there is still time for questions, or if anyone has questions. Yeah, there is a question back there.
It's all pretty scary. So what would you recommend to get into the topic?
It's all pretty scary. Um, it is. Is it scary? Did I scare? Did I? Yeah, I probably did scare you. Sorry about that. What I would recommend is pick a few papers that are introductory material. So the phi failure, actual failure detector, the swim paper. These are papers that do a really good job at explaining these concepts. And then, yeah, the hard thing about education. So there is one very nice thing, and that's more Akka specific maybe, but there is one project by Eric. I will tweet about it. I will send you the link. It takes a rack of Raspberry Pis, puts LEDs on them, okay, and then you see the LEDs with the different colors depending on the state of the cluster node. It's very like educational. You really get to understand what happens. You see the leader jumping from one node to another when you plug in the IP address changes and so on. And there is gonna be a few videos of that online. Or that's what Eric promised me anyway. So that's one of the resources that I would point to, out of the top of my head, because the reality is it's so deep that it's like a rabbit hole, and there is so many different strategies. You've seen it. I just showed a few failure detectors, but they're all very different. So yeah, there is, and it still keeps evolving every day, and so there's many different directions. But these two papers that I just mentioned, and the Lamport paper, please read. Everybody should have read that paper because it's so fundamental. That, or in general, the papers that win the Dijkstra award, the Turing award. Sorry, these are important things, I would say. Yeah. Yeah.
Do you see any innovation in distributed consensus coming from the blockchain community? Any relevant papers, or is it all just a bunch of bullshit?
Should you buy Bitcoin? No. Well, the blockchain itself is extremely simple. That's not innovation, but there are a few things. So Adam Coiler has this thing called the morning paper. Every morning he blogs about a new paper, and there is one paper that he talked about like 3 weeks ago that seems to be doing some interesting advances there in blockchains and distributed blockchains, because there again you have to reach consensus, except that you don't trust anyone, you're out in the wild, you have a problem of having a ton of garbage or like a ton of history to maintain. So there is definitely some innovation in some things, but don't trust. I mean, at the end of the day, for fast systems, blockchain is the wrong technology. Okay, don't go there for real-time systems. This is like blockchain is for slow thing, and I would say in a few, like blockchain is the first generation. If you look at more interesting things like the direct acyclic graphs being used, DAGs, that's what I would look into more than blockchain. Okay, well, if you have more questions, just feel free to come to me, grab me. There's gonna be beers in 1 or 2 hours, I think, and also ping me on Twitter or via my website. And yeah, thank you so much.